in characterization of therapeutic proteins and ligands. Dr. Jayaprakash is currently working with Stelis Biopharma at Banglore. He has done his PhD in proteomics and bioinformatics from University of Delhi, UK. So, welcome.
Thank you. First of all, I would like to thank Dr. Ratnesh and his team for having me here. And so today I'm going to give you an insight into how we can use mass spectrometry for biopharmaceutical applications. Okay, so my talk is going to be spread between a very brief background about Stelis Biopharma and then the evolution of mass spectrometry. It's like some of the Nobel laureates, the key contributors in this field, and then brief about different types of analyzers which are used in the mass specs, and then specific applications on how we can use for characterization of the protein, and then briefly about ion mobility mass spectrometry as well, and then I'm going to summarize. Okay, so with that background, I'm going to start by saying Stelis Biopharma is one of the growing biopharma in the field. So we have a world-class state-of-art R&D facility at Bangalore. So this is housing around 150 scientists, and then you have the manufacturing plant as well as located in Bangalore. So this is also, they are also planning to start CRO related activity as well. Okay, with this, so I always try to acknowledge the great contributions from the scientists in the field, especially the key Nobel laureates. So this mass spectrometry started with J.J. Thomson. So he is the forefather of designing a mass spec to bring in to the perspective of analyzing a molecule or making into charged species and things. And then after that, Wolfgang Paul. So he was the father of the quadrupole analyzer. And then this guy, Francis William Aston, is the person who's analyzed the isotopes of mass spec. And then this Koichi Tanaka, he's very interesting chap. So he was a lab assistant in Shimansu's office, and then he came up with an idea of matrix assisted isotope analysis called Mali-based techniques. So this guy, he's introduced a soft ionization technique. Basically, when you hit the sample with laser, so it just fragments and degrades. Okay, so in order to avoid that, he has came up with an idea called matrix-assisted laser desorption ionization. Okay, so this became so popular in biopharma protein-related field. And then Sir John Fenn, he's the person behind the electrospray ionization. So essentially, so they shared the Nobel Prize for Chemistry of 2002. So basically, the principle behind, so more than 90% of mass spec uses electrospray ionization. If you are wondering what that is, so basically you are introducing a high voltage charge in the spray needle, and then the sample essentially enters into the mass specs, which are getting nebulized, and then because of the high charge voltage, it's getting charged and then enters into mass spec. So all the neutral species gets deflected away. Only the charged species, which is identified and analyzed in mass specs, are captured here. So this was a very great contribution to the science, because of him there is a lot of research going on, because of which we are here at the moment where we are actually. So all the protein field has evolved after the discovery of electrospray ionization. To give some more insight into it, so if you ever wonder, this recent guys like Matthias Mann, and then Rudy Abersol, and then Andrew Shevchenko, all these leaders in the field are somewhere or the other associated with John Fenn. In fact, Matthias Mann was a postdoc in John Fenn's lab. So he's one of the most cited author in the science field at the moment. And then, so again, this guy, so he has introduced this concept of MALDI. So what it does is this laser is drastically absorbed by this matrix and then transferred into protein, and then this protonated species is then identified with TOF chamber or chamber as TOF analyzer. If you ever wonder what are the components of mass spec, so you have an inlet typically from LC. If it is an LC-MS, then it will be an inlet, and then the source, which I have discussed just now, ESI or APCI or any specific applications. It depends upon the types of source you use, and then the analyzers. So this plays a very important role in mass spec actually. This analyzers, it can be like there are many analyzers, but I just specifically focusing on the ones which are most widely used in biopharma field. Okay. And then introduction, and then data analysis, and then interpretation. Okay. So this analyzer, you have triple quad, quadrupole. I mean, you can Google it to check to get the detailed information of all these analyzers. So this is typically used for small molecules, and this one is a TOF analyzer, where you have this. So this is like you can find a pipe kind of things, which I'm going to show you in the later part of the slide, where you have the molecule enters in the TOF chamber, and then it get deflected and identified. Okay, based on the time it travel in the TOF chamber, you get identified with M by Z and the mass. And then the trap analyzer, this is also one of the widely used, and then this is like a 3D trap, which was quite commonly used for medium-sized proteins. And then, so this field of mass spec again, evolution, got tremendously benefited from the discovery of orbitrap analyzer. So this is discovered by a Russian scientist called Alexander Markov. So what he has done is, this is actually a textbook stuff from physics. He just converted into a prototype. Essentially, you have an outer ring electrode and inner electrode. So he just placed in a position in a way that the ions enter in the analyzer. It gets spindled around the pole, and therefore you have a greater accumulation time with greater sensitivity and resolution. You can again check more onto this orbitrap analyzer, which is like revolutionized the field of proteomics research. Okay, so coming to the mass analyzer again. So as I said, like this is the M by Z range and the resolution power of individual mass specs. And as I said, like the data sensitivity and the resolution came with after the with the orbitrap. So right now there are like some 7 or 8 different types of mass orbitrap variants has come. So some of the most recent ones are Lumos orbitrap and so on. Okay. So with this, I'm getting into the biopharmaceutical application of it. So if you are ever wondering like what biopharma companies does, they just select a molecule based on the marketing potential and the application and therapeutic area and so on. And then you have a protein ranging from 3.3 kilodalton, which is manufactured at Stelis, and then it just goes all the way to recombinant MABs, EPO, and recombinant GCSF. Okay, so the thing is, like, if you are thinking that PTH is a very small molecule and it's easily can be studied, and the complexity increases with every increase in the size of the protein. So analytical data that what we generate from the mass spec or any other instrument, that became a foundation for any of the approval of to seek approval from any authority. So how can you study such a complex protein like MABs? Is like when you have a protein and then you just typically digest it with trypsin or a gluci or any other proteolytic enzymes, which just simplifies the bigger protein into smaller units called peptides, and then this is then put into LC and then subsequently tandem with MS. So we have at Stelis, we have Agilent QTOF. And this is the guy, and then so once you get in, the protein is through the LC and MS. So this is what happens. Okay, so you have LC, which essentially separates the proteins which are digested in the sample, and then it just enters into mass spec where you scan for individual peptides, and then each individual peptides are then fragmented with MSMS. So essentially you use a collision cell, and then you just bombard the peptide with inert gas. It just fragments the peptide. Okay, so how it fragments depends upon the type of collisions gas you use and the type of fragmentation technique you use. So if you use conventional CID based technique, you have the fragmentation and CC bond, and then whereas if you use CC and amide bond, and whereas if you use ETD or electron capture dissociation technique, so you have C and Z ions, which is essentially breaking at this specific path. So this is a very useful technique. I'm going to show some data on this as well, how useful it is. Okay, so the products which are produced at Biopharma, okay, let's say Stelis or any other company, so you have essentially you got away with a lot of impurities, right? So you heard a lot of things, a lot of people saying about how you like identify impurities and so on. So this is one of the CQA, critical quality attribute. So whatever impurities which are present above 0.1% should be identified and characterized. So that was the FDA now to launch any drug. So in order to do that, so you need to have a thorough understanding of each and every single impurities coming. I don't know what's happening. Each and every impurity. Say for example, in this case, so we came across some impurities which are like 1 Dalton mass addition. So which is like a very trivial thing. I'm just giving you a very simplest example of deamidation. So this is like if you came across 1 Dalton mass addition, it's very easy to suspect it could be a deamidation. So that's how we start as well, and then we just came up with the. So if you know how deamidation occurs, so the side chain of aspartic acid, which is COOH group, it just constantly swings, and then it just attacks the neighboring amine group, and then it forms a succinamide intermediate with the loss of water. Okay, so this succinamide intermediate, which gives you minus 17 Dalton, and then this one breaks into either asparagine or isoaspartate based on the cleavage wherever it happens. So if it cleaves at here, then it just becomes asparagine, and then if it cleaves at here, then it will become aspartate, isoaspartate. Okay. So characterization of this is relatively straightforward. So I'm just showing you one simplest MSMS spectra. So what you have is, this is the peptide, okay, so upon fragmentation, so you get so actually here I used ETD based technique, because the thing is like isoaspartate cannot be characterized with conventional CID, because you get only A and B ion and C and A and B ion and B and Y ion. Okay, so that's why you cannot identify with conventional CID. So I just subjected to CID based ETD based technique. So ETD is nothing but a. So you use a fluoranthin is the reagent that you use in the use for ETD based technique. So that one just transfers the electron to the neighboring peptides, and then it gets cleaved. Okay, so this based on the cleavage, then you can reconstitute into identify each and individual amino acids. You annotate and identify the sequence of it. So coming to the isoaspartate part, so this is the only species which will be different from the rest of the two spectra, if you can closely have a watch of it. So every single other chromatogram, every other species will be identical, whereas only this guy, so 321, which is the one which represents the third C2 residue, and this is what is identified in the spectrum. Okay, so this is how we characterize. So based on this, and then we will infer that, okay, so whatever we are seeing is deamidated species, or which is respect to aspartate and isoaspartate. So this is one simplest example. Say for example, you get to identify every other day, you get to identify a new impurity, so you will have to come up with a new strategies to identify and to characterize it. So that is one of the major chunk of work which involves mass spec, other than the physicochemical comparative analysis which is done typically. Okay, so after this we identified, annotated these two spectrums are diamidation species. Okay, so coming to the next part of it, my talk. So you were like keep hearing about glycosylations in biopharma, right? So you have a lot of glycosylation variants which are present in the MABs typically. So if you ever wonder, so this is the constant region of MABs where you can see the glycan attached. So this is the simplest form of glycan, and the glycan can be multiple variants. So so this is only a few examples. I mean, there are a lot of variants of glycan species are there. Okay. So this guy, so to show you much more detail how heterogeneous and how complex the glycan analysis is, as you heard from Babu's talk yesterday, it was like mostly very simple tagging and then identification, which Devdev is going to speak after me. But if you are going in depth into it, so each the linkage types and the sugar type will be different. Okay, so this is 1,4 and then 1,6 and then 1,6 and then this is 1,3 linkage type. This is one simple example. And then if you again look at it, so you have 1,6 and then 1,3 linkage type. So characterizing this type of linkage type is very tedious and very time consuming. And also one of the most important thing to note is like any change in the glycan variants can have a very significant impact on the CQA, and then it will have an impact on the efficacy and the toxicity of the drug. So it's very important to characterize. So this is one of the, so if you ever wonder, like, I mean, there are multiple ways of characterizing it. One of the ways is like simplifying it, doing multiple digestion, as like Babu mentioned yesterday. So you will do a sequential digestion, remove one glycan residues at a time, and then go for characterizing using mass spec or HPLC based, fluorescence based technique. So now technology has advanced so much that we can also use ion mobility mass spectrometry. Okay, so this is one of the instruments where you can separate the species based on the folding pattern or the difference in the conformation of the isoforms can be separated. So one of the examples, even the thing with diamidation can be separated with ion mobility mass spectrometry. There are tons of literatures available. Even I tried myself, it works beautifully well. Okay, so the thing is, so you have a conventional inlet and then ion guide, quarter pole, and then these things again, so you can find it in net, and then you can, so this is the separation chamber actually. This is the ion mobility chamber. So basically what you have is an extension of kind of a trap, and then which has a alignment of alternate alignment of lenses guiding the samples in, and then you have an inert gas flows in an opposite direction. Say, so this is an inert gas which can be helium or nitrogen, anything can be used. And then, as I said, so this can be related to an SDS page, conventional SDS page. Okay, the smaller one goes faster than the larger, bigger molecule. Okay, so what happens? Smaller ones migrate faster, and then slightly bigger one slower. Then the other one will be much more smaller. So based on the conformational change, say for example, if the glycan is having a different conformation, and then you can easily get separated in the ion mobility chamber. Okay. And then, so this can be recorded. So based on the thing, so here you can easily find that. So this guy is a smaller one, and then bigger one comes later, and then much bigger one comes much later. So this is how you get to see. And then based on this, you can separate the isoform variants of even glycan or protein or anything. Okay, so so this I have taken one simple example again to show how the separation occurs. So in this paper, actually they have showed two. So this is at 1,6 linkage and this is 1,4 linkage of of an anomeric carbohydrate. Okay, so what they have taken a different proportion. So you have to read from the bottom up, so you can see from here. So this one is 100%, and then the other one is mixed proportionally. You can see both has an identical mass and then identical fragmentation, but if you see the mobility of it, so this is the difference you can see. At some point you can see the complete separation of both the isomeric species of glycan. So this can be very extensively used for characterization of isoform variants. Okay. And okay, so yesterday, if you remember, Amar was speaking about the anomalies in the gas phase of electrospray ionization, right? So it often occurs that you identify a lot of species under a single chromatogram, okay, and then you will misinterpret, okay, these ones are coming only from the single peptide. Okay, under single chromatogram, I'm seeing so many different species of glycan or whatever it is. Okay, so actually it is an in-source fragmentation. If you look closely onto this, so this is one of the examples I investigated using both positive and negative ionization method. So this protonation has notoriously played a very important role in destabilizing this glycan. Especially glycan modifications are very labile, and you can see this fragmentation, different fragmentation pattern of this. Okay, so if you are not careful enough, then what will you interpret? Under single peak, I'm seeing so many different variants of glycan species. Yeah. Okay, so different species of glycan varieties. Okay, so in order to avoid such kind of anomalies, so you have to be bit careful when it comes to this, and then if you see the difference between this, you can clearly make out this negative ionization does not show any in-source fragmentation and so on. Okay, so one more thing with the problem with negative ionization is like you cannot have a very good sequence coverage as you see with the positive ionization mode, and also you cannot perform any ETD on this because ETD electron transfer happens only when you have a peptides with a higher charge state, which is like greater than 2+ charge state. Okay, so for such kind of applications, you have to again rely on positive ionization mode. However, like you can be cautiously interpret such results. Okay, so in summary, what I showed you today, MS is one of the very powerful and one of the most widely used technique in biopharma field for characterization of all the biopharmaceutical products manufactured. Okay, so it ranges from starting from development stage, and then purification, and then character, and then final stability, and then formulation, and everything. So mass spectrometry plays a very important role across. Okay, and then analysis and data interpretation is the very key aspect in biopharma, in the mass spectrometry field, because all you get is a number, and what you make out of those numbers is going to make a very big difference in the result. Okay, and then ion mobility MS is something which is very less explored, and then there is a huge potential behind it for especially characterizing the most difficult to do stuff like isomers characterization and so on. Okay, and then protonation induced modification is something which is real, and then there is a paper from Amar, like in my previous lab, showed like how in source it can significantly modify even proteins and so on. Okay, so one has to be careful about when you analyze and interpret the results. Okay, with this I want to take questions if there is any.
So, what is the workflow of characterizing linkages using ion mobility?
Okay, so characterization of linkage is a very interesting thing. So, especially when you have a disulfide bonds and things. So, ion mobility mass spectrometry is going to be a very conventional one with an extra degree of separation using in ion mobility chamber. Say, for example, if there is a normal disulfide linkage, one single linkage between two peptides, it's very straightforward. So it gets separated and then fragmented and then identified using MSMS. Whereas if you have a disulfide scrambling, let's say two peptides having two linkages, okay, intra and inter linkages. In such case, there is a possibility of disulfide scrambling, right? So that again, everything is going to be same. The mass, MSMS is going to be different, and interpreting is also a tedious thing. Okay. Whereas in ion mobility master, if you have any disulfide scrambling, you can easily get separated, and then okay, you can already imagine. Okay, there is something which is conformationally different from the major species, or the one which is coming at the same retention time. So I have to be carefully at it, or I have to look carefully onto the things, and then you essentially do an MSN basically. With only MSMS, you cannot characterize disulfide scrambling. For that, you have to do MSN, which is essentially MS3. You have to go one step further, and then taking the specific ion, linkage specific ion, and then you have to fragment at MS3 level, and then look for the modifications.
But so that sequential dilatation has to perform, right? Then only the detection.
Achha, you are talking about glycan. Okay, so glycan. Okay, so whatever I was talking about when you said linkages, it was on related to peptides. Okay, so if it is a glycan specific thing, so there are two ways. As I said, one, you can sequentially digest with different enzymes and then look for the modifications. Right. The other way is, so you essentially do only MS and MSMS, right? So you have two different types of species coming at given retention time. Okay, these two can be an isoform variants, as I mentioned, and then you do MSMS. And then the only way to interpret this is doing, I mean, if you see a glycan cleavages, the fragmentation function, I don't have it in my slide, but you can easily find it in net. Okay, so the thing is that the cleavage, wherever it happens, right? So the ions between X and Y ion has to be thoroughly represented by head-to-head comparison with 1,6 and 1,4 linkage, for example, for that sake. So you have to be very carefully start annotating one by one, and then you will essentially find that linkage difference.
So it is getting separated based on conformation only.
Yes. So one way is conformation, the other one is MSMS, of course.
What strategies do you use to confirm in-source fragmentation or control any, apart from excising them, if you extract the sequence?
So there are multiple ways you can confirm in-source fragmentation. So one of them is, while we found very efficient, is altering the cone voltages in the MS. Source voltage and cone voltage plays a very important role in in-source fragmentation basically. So you just change the voltage, say if you start with 35 or you go all the way to 50, 80 and so on, and sometimes you just reduce and increase, and then you see the variations in the fragmentation basically.
That is fine.
Yeah, let's take a very simple peptide and then which has a 1 plus charge, okay? That doesn't have so much modification than 5 plus charge, right? If you have a higher charge state, the extent of modification is higher. Even at say 3 plus charge, you tend to see a succinamide, in-source succinamide formation in the peptides which has asparagine, and even pyroglutamate formation at when you have a free N-terminal glutamate.
So in-source oxidation also possible, no?
Exactly, it is very much possible.
So how to control that?
So controlling is again, so it depends upon the types of applications. So
what is the reason behind that?
That's because of the inherent nature of mass spec. So that's because you are subjecting your protein to high voltage, and then you are nebulizing it to ionize the protein, and then you are essentially spraying it.
Because all are inert gas we are using.
Of course, yeah. Ideally, it should not happen, but it happens. That was the identification. So there is an ASMS paper from Bicon, where my previous lab. So you can refer to it. There is this modification is real, and then we observed it across multiple molecules. And then when the increased charge state.
So how to differentiate that? It is a in-source oxidation or the real oxidation?
Okay, so oxidation is something which happens in much lesser phase than other modifications. Okay, so if it is if you have an oxidized species, okay, that is adding some charge to the peptide or the protein, right? So essentially, in LC, you can have an easily separation of oxidized species than the non-oxidized species. Okay, so you get a two different
So
peaks.
if it is in-source oxidation, then we will not get any peak in LC, right?
No. It's only coming from the source as a cone, when it sprays.
So the oxidation that we discussed yesterday, if you do that, then it gives you a way to differentiate between the two. Whether it's in source or it's actual oxidation of the molecule.
So adjuvant is using which inner pairs?
It's all nitrogen. It's all
Nitrogen.
Yeah. It's,
What are using argon?
it's slightly expensive. So
Nitrogen.
majority of the mass specs preferred is all nitrogen. Yeah. Okay, if there is only so much, thank you.
Thank you so much, sir.
Yeah, thank you.
Is it open of conversation or you would like to call briefly?